Okay, so we are now live on YouTube, so we can start the.
Okay, so good morning everyone and welcome to this Zoom webinar on CCUS scenarios for the cement industry. It's a pleasure to welcome you. Although I have to say this is not the form of meeting that I prefer, I tell you honestly. We all know the situation in which we are, so we are forced to keep the meeting by remote without being personally present. If this is, I think, the good way to do, given the current circumstances, I think, and I hope to express the wish of everyone connected here, that this type of communication and interaction is going to end or to be used much less, at least soon, so we can get back to normal. My name is Stefano Consonni. I am a professor of energy systems at the Department of Energy of Politecnico di Milano. And it has been a pleasure for me, starting a few years ago, to be involved with several of you who are connected today, starting from Alla Shogenova from the University of Tallinn and her collaborators, with whom we started a very fruitful and stimulating for us interaction in connection to our Cleanker project. I guess that most of you are familiar with this project, but in the first presentation that Martina, who is the coordinator of the project, will give you, Martina will remind the basic features and objectives of the project. Cleanker was started to give an answer to a question and to an issue that it is crucial for the future of the cement industry in an age that will be more and more constrained by the need to limit the emission of greenhouse gases and to reduce the impact on expected climate changes. And within this framework, we included in Cleanker a specific work package to look at and analyze the large picture of what is going to be the scenario in which the cement industry and more general industry will have to live and hopefully to continue to grow while coping with these constraints on CO2 emissions. And this is exactly the topic that we will cover in this webinar. We will have three distinguished speakers from the University of Tallinn, and we are glad of their contribution and their participation to this webinar. I am sure that this will add to all participants, both in terms of knowledge and in terms of also of interesting and stimulating questions. I guess that you all have the program of the webinar. We started nearly on time, and we will go on until 12 o'clock with the presentations. We will have first an introductory presentation by Martina Fantini, the coordinator of Cleanker, and then two presentations from Alla from the University of Tallinn, then again from the University of Tallinn, one presentation from Mustafa Sem Usta, one more presentation from Kazbulat, then back to Alla, and finally the last presentation scheduled at 11:40 from Kazbulat again, and the conclusion from Alla. From 12 o'clock on, we will have half an hour for discussion, and I thank you in advance for the contribution that you will give in this discussion. One of the purposes of this meeting is not only to present material, but also to put on the table what are the issues that we think we'll have to face. More generally, I'm talking about the cement industry, and discussing and having an interaction on how we can cope with this issue, I think will help all of us in making a step forward. So thanks again for being here this morning, and let me give the mic to Martina for this introduction on the Horizon 2020 Cleanker project. Thank you, Martina.
Hi, hi to everyone, and thanks, Professor Consonni. I am Martina Fantini. I will give you an overview of the Cleanker project. Can you see my presentation? I think so. I hope that a great part of the audience already know about Cleanker project, because it started at the end of 2017, and I would be a very bad coordinator if the most of you wouldn't know or wouldn't have heard about this project. The main goal is to advance the calcium looping process for CO2 capture in cement plant, and the core is the demonstration at TRL7, that means in industrial environment, of the integrated calcium looping configuration. As said, this project is an Horizon 2020 funded for about 9 million euros, and more about the half of this amount went to the engineering and construction of the demonstrator. This demonstrator has been built in the Buzzi Unicem cement plant located in Vernasca, that is close to Piacenza, that is close to Milan, so in the Po Valley in northern Italy. Here you can see the cement plant below on the left. So this is the Buzzi Unicem cement plant where our demonstrator has been erected in the last months. We are 13 partners, 5 from EU member states, plus Switzerland and China. And the partners has complementary skills both on modeling and on experimental activities in order to reach the main goal that we have. You can also see that this is a capture project, but we have a lot of work packages also devoted to other activities. Indeed, in the first time, at least in 2017, this was the first time for a project, European project focused on capture, that included the full CCUS value chain study. In particular, there is a work package totally devoted to this activity. And the tasks includes the techno-economic modeling of CO2 transport, storage, and utilization scenario, the CCUS regulatory issues in order to understand the gaps in national regulation, the definition of Buzzi and Italcementi cement plant, these two cement users, because they are a partner in Cleanker. So the definition of the Buzzi and Italcementi cement plant suitable for a first of a kind CCUS plant based on transport and storage opportunities, and also the experimental activity for mineral trapping of the CO2 reuse in concrete. So a very strong consortium to reach a very important goal. I always like to start with this sketch because in 2017, Cleanker in our project proposal was just this drawing. And after the first year and half, after the effort of the partner devoted to the engineering of the demo system, the flow sheet became a bit more complicated. This is the rendering of the demo of the demonstrator that has been was to be placed in the cement plant in Vernasca, here in the preheating tower. And this was a picture of 2016 where we were preparing the project proposal. The rendering and the rendering of the integration. After more than 3 years, we have done, of course, a lot of works in the characterization of the raw mill at lab scale, engineering, construction, modeling, etc. And we have completed the erection work last autumn. In particular, here you can see the cement plant, a view of the cement plant. The calcium looping technology basically is the loop of calcium between two reactors named carbonator and calciner. Here in the picture on the right, you can see the view of the carbonator, and here on the left, you can see the calciner and the integration in the preheating tower. In autumn, in 2020, we had also the opening event that, of course, with the restriction due to the situation, and we had the cut of the ribbon. So the commissioning is completed, and from the point of view of testing, we are ready to start the experimental campaigns. In the presentation, I have also this slide. I will upload then the presentation in the website. So if you are also interested in the documents, the public documents available, you can follow these links in Zenodo and in the website, and then to download the documents you are interested in. This was my introduction, and I leave the floor to the chairman for the presentation of the real speakers of today, our friend from Tallinn. Thanks.
Thank you, Martina, for the introduction. I have to apologize with Martina because when I gave her the mic, I didn't record very briefly her current position. I'm sure that most of you are familiar with Martina, but for those of you who are not, let me just inform you that Martina is currently a research scientist and a research manager at LEAP, which is the Laboratory for Energy and the Environment in Piacenza, a research company which is participated by Politecnico di Milano. Martina, we had the pleasure of having Martina as a PhD student at our Department of Energy at Politecnico. Then for some time, she went off to Technical University of Delft. And then we captured her again and we got her back at LEAP, where she's now coordinating the Cleanker project and following a number of activities related to national and international calls. Thank you, Martina, again. But let me move to the first presentation that will be an overview of the role of CCUS by 2070, so a long-term perspective based on the CCUS report by the International Energy Agency that just came out. The presentation will be given by Professor Alla Shogenova, who is a senior researcher in Tallinn University of Technology at the Department of Geology. Alla is a very energetic and strong researcher leader and pioneer of CCUS research and education in Estonia. She has been the supervisor of a number of PhD and master theses on CO2 geological storage, and she coordinates the Estonian research group on a number of international projects, starting from the Framework 6 project, European project, GeoCapacity. In 2020, she was one of the professors of the ENOS project, International Master Course on CO2 geological storage. We have been very glad to involve Alla in the working group of our Cleanker project, not only for the energy that she puts in it, but for the substantial contribution that she's giving us on a number of very relevant topics. So please, Alla, the floor is yours. Well, actually, the mic is yours with the first presentation.
Thank you very much, Stefano. We decided to make such introduction to emphasize the importance of CCUS, not only now by 2050, but also by 2070. And it is based on the report published in September 2020 by International Energy Agency. It is a special report on carbon capture, utilization and storage. And in this report, analysis of IEA showed that CCUS is one of the key technology areas to put energy system on a sustainable way to meet international climate goals and to reach net zero targets. And it is carbon capture, use and storage. It's only a group of technologies that can both reduce emissions in key sectors like industry, like power industry, power production, but also to remove CO2 emission, which cannot be avoided from point sources. So today, there is only around 20 commercial CCS projects worldwide, but there are plans available for 30 commercial CCS facilities, which has been announced recently in different countries in Europe, United States, but also in other parts of the world, like Australia, China, Korea, Middle East, and even New Zealand. And projects now, even last, before September 2020, there were decision to investment around 27 billion United States dollars. We know that during last half of the year, additional investment decisions also came. So this number now is definitely higher. So also cooperation across borders between governments and industry are critical if CCS needed to meet energy and climate goals. And markets alone will not turn CCS into the clean energy success story, but governments and industry today have the chance to combine their forces and to realize environmental and economic benefits of CCS. So there are mentioned in the report, it is mentioned at least 4 strategic areas. One is tackling emissions from existing energy infrastructure, that CCS can be retrofitted to existing power and industrial plants, and that could otherwise 600 billion tons CO2 could be avoided over the next 5 decades. So solution for the second strategic area is that CCS is solution for some most challenging emissions. For example, heavy industry accounts for about 20% of global CO2 emissions today. And only CCS can be solution for deep emissions reduction from cement production. And it is also most cost-effective approach in many regions to avoid emissions from iron, from steel industry, from manufacturing. And captured CO2 is a critical part of supply chain for synthetic fuels from CO2, for hydrogen, and also for transportation and aviation. Another strategic area is cost-effective, that CCS is a cost-effective pathway for low carbon hydrogen production. So CCS can support rapid scaling of low carbon hydrogen production to meet current and future needs and their application in transport, industry, and buildings. And the last strategic area, it's for CCUS, it's removing carbon from the atmosphere. And we have emissions which cannot be avoided directly from point sources, as we do at the power plants or at the cement plants, but also for these emissions, CCUS is an important approach, and it can help to deliver net zero energy systems. In transition to net zero emissions, the role of CCS also evolves and extends to all parts of the global energy system. In International Energy Sustainable Development Scenario, in which global CO2 emissions from energy sector declined to net zero only by 2070, the initial focus on CCS is on retrofitting fossil fuel-based power and industrial plants and supporting low carbon hydrogen production. By 2030, more than half of CO2 captured is from retrofitted existing plants. For example, we know that there are many new plants which are now just built or during building process, so we can continue using them, and they could be carbon neutral, but only if we apply CCS. So our focus, the shift will, the focus will shift to CO2 capture from bioenergy and air removable CO2 from air, then source of climate neutral CO2 for synthetic aviation fuel, and in 2070 scenario, around 60% of captured CO2 is linked to fossil fuel, and the rest from industrial processes, bioenergy, and the air. So the faster transition to net zero increases the need for CCS, which accounts about 15% of the cumulative reduction in emissions in sustainable development scenario. So moving to the net zero goals from 2070 to 2050 would require almost 50% more CCS deployment. So generally, this is a figure which demonstrates the share of CCS in sustainable energy scenario. And this is a graph until 2070. We can see that role of CCS is increasing by 2050, 60, 70. With time, it's increasing, and the share in these cuttings is 15%. Also, 1/6 of cumulative emission reductions in 2070, it is CCS. Also, carbon removal plays an important role in net zero transitions. Technology-based carbon removal are needed to balance emissions that are technically difficult to or expensive to eliminate. And when net zero emission is reached in CDS, then still about 3 gigatons of emission remains, and this is notably from transport and industry sectors. And these emissions could be captured from bioenergy and the air and stored underground. And direct air capture technologies have significant potential to accelerate the transition to net zero, but we need to decrease costs. So the capturing directly from the air and storing is alternative to capturing it from bioenergy. So direct air capture plants are already operating in small scale, in pilot scale. Costs are currently high. So, but with further innovation, it will be very important option. And if other technologies will be not yet commercially available. And so you can see how CO2 emissions will be captured with CCS in sustainable development scenario. So you can see that now in 2020, the total CO2 emissions in the world is more than 33 gigatons. In 2030, after applying CCS and all measures, we will still have 27 gigatons. In 2050, we will not come to zero. We will still have 9.4 gigatons. And according to this scenario, the net zero, carbon zero society will be possible only in 2070. And what is interesting, that in this scenario, only 10% of CO2 is possible. In 2050, in 2070, only 10% of CO2 is possible to use, but all other CO2 we have to store. So generally, around 60% of CO2 captured in up to 2070 is from fossil fuel use. The rest is from industrial processes, bioenergy, and direct air capture. And this reflects difficulties to eliminate CO2 emissions in some industry sectors and in cement sector, and also the role of biofuels and direct air capture will be increasing also in production synthetic aviation fuels and in removing CO2 from the atmosphere. So the fossil fuel still the source of about half of CO2 captured in 2070, and around 1/3 of this from low carbon hydrogen production from natural gas. So when net zero emissions are reached in 2070 in sustainable development scenario, so 9.5 gigaton is captured and stored, and all another is captured and used. So the power sector accounts for around 40% of the captured CO2 in 2070, but half of this is linked to bioenergy, and 1/4 of CO2 captured is in heavy industries. Almost 30% is in the fuel transformations to produce hydrogen and ammonia from fossil fuels. Also CO2 captured from biofuel plants and is used to make synthetic fuels or stored for carbon removal. So the next 7% comes from direct air capture, and only around 8% of total captured CO2 is used or recycled. And it plays, so I told that 10%, but less than 10%, around 8%. It plays an important role in the decarbonation of the transport and industry sectors through the production of transport fuel and as feedstock for the chemical industry. So generally, this is, we can see the proportion of sources in sustainable of CO2 capture by source and period in the sustainable development scenario. So we can see that the role of CO2 captured from coal is increased, from natural gas also in 2050. This is blue from industrial processes and biomass in green. And when we come to the 2070, we have increasing role of biomass, and industrial processes have smaller share compared to direct air capture and compared to biomass. But natural gas, role of natural gas becoming higher, and of coal is smaller, but still are available. And so this is the same figure for Europe. So we can see that now we know that the European Commission still concentrated on the CCS for industry, but in 2050 we will have CCS for fuel transformation, for industry, and for power sector. And in 2070 for power sector it's increased, but of course with share of biofuel and large share for industry and for fuel transformation. So generally, 4 high-level priorities for governments and industry would accelerate and promote CCS over the next decade. So there is 4 points: create conditions for CCS investment, target the development of industrial hubs with shared CO2 infrastructure, and identify and encourage the development of CO2 storage and boost innovation for critical CCS technologies. So generally, this presentation is based on the International Energy Agency report. So I'm finalizing this, and I have to move to the next presentation.
Okay, thank you, Alla. The next presentation will get more specific on the Cleanker project. The title is The Integration of Buzzi and Italcementi Heidelberg cement plants into the first operating CCUS cluster projects worldwide. The presentation will be given again by Alla, and in order to comply with the schedule, Alla, you have, well, actually, in theory, a time which is too short. You should finish at 10:40, but I'm sure that you cannot make it. But let's say I would be thankful if you could stay within 12 minutes in the presentation. Thank you.
Okay, thank you very much. I will try. So generally, it was this work was made in the Cleanker project as one of the work package 7 tasks. We had to define suitable Buzzi cement and Heidelberg cement plants worldwide for integration in the worldwide CCS cluster projects. And initially, it was planned to integrate cement plants in 12 cluster projects reported in International Energy Agency Greenhouse Gas Report 2050. So from that time, some projects were stopped, new projects started. So finally, we made integration of 12 cement plants into the 12 worldwide projects. Methodology of this work was that we collected data into the database from 12 projects: geological, technical, CO2 emission, transport data, and also we collected data from the cement from the Buzzi and Heidelberg cement group cement plants from these countries, and we needed to define the best suitable. I will start with some details for some projects. In North America, we mapped 4 projects, 1 in Canada and 3 USA. So in Canada, Alberta Carbon Trunk Line project. It is a very interesting project because it used CO2 emissions from 2 emission sources, and which will be could be transported along the pipelines available, large diameter pipeline, 16 inches, and the distance of available CO2 pipelines 240 kilometers, and the CO2 storage is planned in Clearfield in Alberta. So this project reported that last year that they are ready, all operations, and storage is planned in the Leduc Formation Nisku Reservoir at the depth about 2 kilometers. So generally, the annual capacity of pipeline is about 15 million tons, and they will give access to all producers in Alberta Industrial Hub. And so in 2019, North American subsidiary Lehigh Cement announced a feasibility study of full-scale CCS project, and they started to develop pilot capture plant at Edmonton, and this plant is located 170 kilometers to storage site. So we can say that one cement plant is already integrated. There is very good plans for integration of one cement plant. Piloting is already started for the RCTL cluster in Canada. And in United States, we mapped 3 projects, which is Rocky Mountain, Denver City project, and Gulf Coast project. And so we identified the cement plants close to these projects. All these cluster projects in United States are using CO2 for enhanced oil recovery. And I would like to show some details, more detailed map. This is Rocky Mountain cluster, and they have at least 6 operating CO2 enhanced oil recovery fields. They use annually more than 10 million tons CO2 capture, 2 gas processing plants, and the Mason City Lehigh Hansen cement plant could be integrated, but location is not very close. It is about 1,200 kilometers. So in the Denver City cluster, large project with already used 45 million tons of natural CO2, more than 8 million tons captured by 3 plants. You can see this 1, 2, 3 plants. And there is at least 6 depleted oil fields which could be used. These all projects which I'm speaking about in United States are operating for many years, successfully operating. And for the Denver City cluster, the Marine cement plant is located at the good distance, only about 81 kilometers from Ccus oil field, and it could be integrated in this cluster. So the Denbury owned Gulf Coast project located in 3 United States states. There are 20 operating and potential oil fields, and the San Antonio cement plant is located at the distance about 280 kilometers and could be integrated. So generally, the best for United States, we found 3 cement plants for 3 operating cluster projects with enhanced oil recovery, with using CO2 for enhanced oil recovery, and the best location is for Buzi Unicem Marine plant. So we also made one project, mapped one project in Australia. It is CarbonNet project, which we mapped instead of Collie project in Australia. The Collie project was cancelled because they did not find suitable cap rocks in the storage site. But the CarbonNet project is in good developing phase. They have Pelican storage site. They have already drilled. They're drilling injection well there. This will be offshore storage, and this site, known as Pelican, has good capacity, at least 125 million tons. They have already 3 injection well and 1 observation well. And cement plant is located close. The most closest is Heidelberg, partly shared by Heidelberg Cement and Holcim Australia Railton plant, but it's located in Tasmania. But the distance is by ship will be about 350 kilometers, but also 20 kilometers on shore by pipeline. So if we go to the European project, so the most people interested in CCS know that the most advanced in Europe project is the Longship project with Northern Lights infrastructure in Norway. And this is the only one in the world project which already include Northern Breivik cement plant. We mapped it because it is very close to another developments, which is in Sweden, in Denmark, and this another project in Denmark called Skagerrak, and they can develop a storage site offshore Hanstholm. And in these interesting locations, the Skövde cement plant from Sweden could be integrated with Skagerrak cluster or more distant located Northern Lights project. So we also mapped Porto's project in the Netherlands. The Porto's project replaced the road project. Now there is no in the Netherlands any one cement plant which could be integrated, because 3 available cement plants in the Netherlands, they are not producing clinker anymore, so the technology of clinker could not be applied. But the cement plant Ccus in Belgium is located very close. It is only 225 kilometers from onshore CO2 pipeline of the Porto's project. And the Porto's project is planning to make storage in offshore depleted gas fields. And very interesting country for cluster projects is United Kingdom. In United Kingdom, we mapped 3 projects, which is net zero Teesside, zero carbon Humber, and HyNet. And this net zero Teesside and zero carbon Humber, they are planning to make storage now in the Endurance offshore Saline aquifer storage site together. And we identified Heidelberg cement keton cement plant, which could be integrated, and the storage could be CO2 could be transported from this plant to the Endurance. But the most exciting proposal was to integrate to the HyNet project, which is planning to produce hydrogen. And we propose to integrate 2 cement plants, Bateswood and Ribblesdale, which located very close, 50 kilometers and 85 kilometers. And we are very glad that we sent our recommendations from this project to Heidelberg Cement group, and they took decision and signed already agreement with HyNet project that they will develop that Bateswood cement plant will be integrated, will work together in the HyNet project. So the information from Heidelberg Cement came in beginning of March that they will make feasibility study, and the Bateswood cement plant will be the second cement plant in Europe integrated in the CCUS cluster project after Northern Lights, of course. So we also mapped Basca project in France. It was studied, but now the good news that now in France, the Vasco 2 project is under development, and this location, this cluster is one of the perspective in France for the further development. And we propose cement calcite cement plant for integration, which is about 50 kilometers from the Alberon storage site. So conclusions that we mapped technical and geological parameters of 12 large projects were included into the database and integrated with 12 Heidelberg cement and Buzi unit cement prospective for clinker calcium looping technology exploitation. technology. So the distance from cement plants and maturity of the project permitted to propose priority for possible integration. So we found the most suitable projects in United States, in Europe. They are located in 50 to 300 kilometers to storage site. And the Bateswood cement plant, which has the closest location in the UK clusters in the HyNet, was already joined consortium of HyNet Northwest cluster project. And all the cement plants which we proposed, they are producing clinker and cement and suitable for exploitation study of the clinker project. So thank you very much. Sorry that I'm a little bit longer than I had time.
No, that's okay, Alla, that's okay. You took 2 and 3 minutes more, so that's okay. I think we are close to schedule. Thank you for the interesting overview of cluster projects, both in the US and in Europe. And let's move to the next presentation, which will be on mineral sequestration of CO2 from Bernasca sea looping demo system scaled up to a pilot. The presentation will be given by Mustafa Usta, who is a second-year PhD student at Tallinn University of Technology, more specifically at the Laboratorio of Inorganic Materials. Mustafa graduated from the master's program of Environmental Engineering and Management at the Tallinn University of Technology. His current PhD topic entails the utilization of alkaline solid waste in carbonate-bonded lightweight construction materials. He's the author of 2 publications related to mineral carbonation and utilization of industrial alkaline waste, and he's involved also in the Cleanker project as a participant to the activity envisaged in the work package number 7 on CO2 transport, use, and storage. Before giving the mic to Mustafa, let me remind all of you that if you have questions, you can write them directly in the section on Zoom question and answers. And if they are very specific to the presentation, we may address them right away. Otherwise, there will be time to address them after 12 o'clock in the half hour that we have set aside for discussion. So please, if you have questions, start writing them already, and we'll keep them in mind. Please, Mustafa.
Thank you. I hope you can all see very well. So today I will be talking about mainly the laboratory testing and preliminary testing of mineral sequestration of CO2 for Bernasca calcium looping demonstration system. So the main goal, as it was mentioned before, is to demonstrate the mineral sequestration of CO2 in pilot scale and utilizing recarbonated wastes in concrete application later. So for this reason, the laboratory tests were carried out to specify the recommendations for a pilot design and to identify the most promising materials and industrial wastes for CO2 capture. Also to build a respective mathematical model for generalization of the data and for preparing input for process upscale, which I will not be going into detail in this presentation. So you can see a rough visual of the calcium looping demonstration system here. And as for the waste that are used, several types of waste were collected from different industrial sectors and characterized for their CO2 binding ability. So these include burnt oil shale samples, concrete demolition wastes, cement bypass dust, as well as blast furnace slag from steel industry. Burnt oil shale samples were quite promising, but unfortunately the concrete demolition waste samples were not, which I will be going into detail later. But here you can see the free lime content, which is the main contributor for the mineralization, is non-existent in concrete demolition waste as it is in the burnt oil shale samples. So therefore, the samples also added other samples such as cement bypass dust and blast furnace slag to see the potential. And here you can see the phase composition of the different samples that are have been used in the laboratory tests and their CO2 theoretical maximum values and already existing mineral CO2s inside these samples. So, according to previous studies that are done by our lab as well, the pulverized firing ashes from power plants are characterized by lower specific surface area, and the circulating fluidized bed ashes by higher specific surface area. And here, most of the samples from burnt oil shale ash varies between 2.55 meters square per gram and 6.05 meters square per gram. The mean particle size of the total ashes are similar to electrostatic precipitator ash of the same boilers. There are total ashes and electrostatic precipitator ashes in these burnt oil shale ash samples, with the exception of the BOS 6 sample, which has an exceptionally high particle size as it is indicated here. As for the scale of the laboratory experiments, they were conducted in firstly 1 liter intensive mixer using low water to solid ratio of 0.2. And later for process upscaling, 46 liter concrete mixer equipped with gas inlets and outlets was utilized. The operation conditions such as CO2 content in gas phase, rotational speed, and material flow was varied during the experiments in order to see the parameters effect on the process. So here you can see the concentrations of calcium carbonates and portlandite, and since the CO2 uptake was mainly attributed to free lime content, which is relatively high in burnt oil shale ash samples and cement bypass dust, which is not shown here, but non-existence in concrete demolition waste. As you can see, the concentrations of portlandite and calcium carbonate are not changing as there is not enough non-existent free lime in the concrete demolition waste, and blast furnace slag as well, which is not shown here in order to not complicate the graphs too much. Comparing different type of burnt oil shale samples indicated that free lime content was fully utilized in the case of electrostatic precipitator ash from circulating fluidized bed boilers, which is mainly what is used in the power plants today. And free lime in coarser total ash and less porous pulverized firing ashes was only partially utilized. And the effect of the mixing speed as well as the concentration were not as visible, meaning that they did not really affect the process. As for the changing parameters such as flow rates of both gas concentration and the mass of the samples, indicated that they can accelerate the CO2 mineralization process due to improved contact of the phases up to a point. As you can see here, while the mass increased, the reactor efficiency and the carbonation degree has increased up to a point, as well as when the gas flow increased. These are again in the first phase of the 1 liter intensive mixer. And for the experiments in a modified concrete mixer, indicated that in comparison with the 1 liter intensive mixer, results are comparable, which shows that upscaling with this type of apparatus is suitable. And the preliminary tests that are done in Italy were put into practice. A CO2 gas stream was artificially prepared by mixing CO2 and air and in different concentrations, allowing to vary CO2 concentrations. The 200 liter pilot was designed based on a commercially available concrete mixer integrated into calcium looping demo system. And equipped with inlets and outlets, as well as CO2 temperature and moisture sensors to detect the reaction progress. So solid samples were collected after every 10 and 30 minutes and submitted to thermogravimetric analysis for quantification of calcium carbonate as well as portlandite. And you can see the graphs on the right that the results indicate that the system saturated after 2 hours as portlandite became depleted and the calcium carbonate stabilized. So from here, it can be said that preliminary testing confirmed that the CO2 can be mineralized from a gas mixture by burnt oil shale in proposed wet conditions. As for the, if we summarize what we have, the results show that the binding capacities can go up to 0.18 kilogram for oil shale ash and 0.14 kilogram for cement bypass dust. And the CO2 sequestration tests in larger 200 liter concrete mixer that are done in Italy confirm that the applicability of wet carbonization in larger scale. And the laboratory tests show that free lime content can be exhausted within 30 minutes in a high CO2 concentration. And the overall environmental problems are not seen by such as sulfate leaching, since we use a low liquid to solid ratio. These calcium sulfate and other sulfides are not detected in the tested samples and products. So that is all for me. Thank you.
Thank you, Mustafa. Thank you so much also because we are back to schedule. We saved a few minutes in your presentation. Thank you so much. We have a question that we can address right away. Nicola Mandelli asks in which laboratory and where you conducted the lab scale CO2 mineralization test. Maybe right away.
The main laboratory tests are done in Tallinn University of Technology, Laboratorio of Inorganic Materials, as all the systems are located within there. But the preliminary tests with the 200 liter mixer were done in Italy, which the exact location I'm not sure, but the colleagues here might know better from Italy.
Well, I guess that this is located in Bernasca, right?
Yeah, probably, yeah.
Okay, so I can add one question myself. So the setup for the experiment in Vernasca, is it ready? And when, or maybe also Alla can answer to this, when are we planning to carry out the tests scheduled in Vernasca with this?
These tests are ongoing.
Okay, very good.
Yes, they are ongoing.
Very good, very good. And so there will be a time, maybe the second half of the year or at the end of the year, where we'll present the results of these tests, which is part of the program of Cleanker.
Yes.
Okay. Very good. I see no other question. So, as I said, we are right on time. Let's move to the next presentation, which will be on the North Italian CCUS scenario for the cement industry. And the presentation will be given by Kazbulat Shogenov, who is a researcher in Tallinn University of Technology at the Department of Geology. He has participated in a number of international projects on CCS. He defended in 2015 the first PhD thesis in Estonia on CO2 geological storage, which included 3D geological, seismic, and experimental modeling of CO2 storage in Baltic structures, and this was in cooperation with Italian and French colleagues. Kazbulat is an author of innovative scenarios for the Baltic offshore structures for CO2 storage, and he is actively disseminating CCS information in Estonian media and social networks. In Cleanker, as for Mustafa, he is a participant and contributor to Work Package number 7 on CO2 transport, use and storage, and he is the developer of the ArcGIS database and author of a number of deliverables and publications. Please, Kazbulat, go ahead. Thank you.
Hello, everyone. Please tell me what do you see, because I'm trying to share only the presentation without split my screen. Okay.
I think it's okay. We see that, at least myself.
Yeah, perfect. Thank you very much. Hello, thank you for a nice presentation of me. It is a big pleasure for me and great honor to present the Italian scenario. CCUS scenario for cement industry. So some words about introduction. All data for possible Italian CCUS scenario was collected into ArcGIS system. The data include location of samples collected and studied in CO2 mineral carbonation experiments and their results, location and parameters of 3 cement plants, including Buji, Unicem, Vernasca, and Robelante, and Heidelberg Cement, Italcementi, Chalusco, Dadda plant, and location of the possible CCUS sites in Malossa, San Bartolomeo structures and their parameters. CO2 mineral carbonation plants were not included into the scenario because the results of the experiments and collected data demonstrated that either binding abilities of the studied waste material wasn't enough. It was less than 1% of annual produced CO2 by Robelante cement plant. So that's why it was avoided. Here you can see location of studied enterprises. So Buji, Unicem, Vernasca, cement plant, Heidelberg cement, Italcementi plant, Cementeria de Calusco Dadda, one of the largest cement plant in Europe, and Buji Unicem is the second largest industry player in the country. And also you can see the location of studied structure, Malosa San Bartolomeo. So the northern Italy has good options for CO2 geological storage, including Lombardy region. Previous studies made in Italy for CO2 geological storage have determined the potential suitable reservoir rocks represented by upper Messian Serignano gravel conglomerate. CO2 storage capacity of this Serignano formation gravel reservoir is a study area shown here by pink circle, was estimated as 320 millions of tons of CO2. CO2 storage is not permitted in Italy in seismic high risk areas. Here you can see the location of Malosa structure. You can see that it's located between two high risk seismic areas, but the location of Malosa structure is in low risk area. So Malosa structure located in central part of the Po Valley or in Lombardy region of northern Italy. So here you can see some geological background. We have good cap rock with the thickness in average 500 meters. And according to the data from the 18 wells, the average thickness is 400 meters. So the formation is Santerno clay formation and composed of clays with quartzitic sun interlayers with average porosity of 6% and permeability 0.1 millidarcy. The reservoir is Messian Serignano gravel conglomerate formation, average depth 1,200 meters and thickness of 200 meters, and about according to the data from the 18 wells studied in the study, the average thickness is 83 meters. And the structure composed by polygenic conglomerates with some interbeds of sands, clay, and sandstones. The porosity, average porosity 26%, and permeability 400 millidarcy. So here you can see also data collected from each of 18 studied wells, and average geological petrophysical properties of structures. So data of CO2 storage site was collected from VDP, which is a public database available in the web. For the selected CO2 geological storage structure, 18 old wells were available from Malosa from 1 to 5 and 7 to 14, Malosa A and B, and Caserate 1, 2, and Cassano Data. You can see it's here, yeah, in this circle. All of the available data were evaluated to create the 3D static model of the Malosa structure. The analysis of the contour maps of the reservoir top and the thickness contour map taken from the Clausi allowed us to reconstruct the different geological formations. After that, this 3D geological model has been elaborated by Petrel. So I will not focus on details of the modeling. You can see here some results of our models. The average porosity estimated by Petrel was 26%, Alters is a range of 12.5 to 38%. Here you can see the table of updated table with parameters after 3D modeling in Petrel. So CO2 storage capacity was estimated with different levels of reliability, called as optimistic and conservative approach. For optimistic approach, we used approach described by Bachu et al. 2007, and for the conservative approach, we used the simulation based on Monte Carlo and presented by US Department of Energy. And for you can see here the formula. For optimistic approach, we took the storage efficiency factor of 10 because our structure is bounded by faults from two sides, and but according to our estimations, the net to gross ratio, we decided to choose a low quality reservoir parameter of 10. And for conservative approach, we choose 4% for the coefficient, storage coefficient. Here you can see also the estimation of in situ CO2 density in the reservoir conditions. And here is the result of our estimation. So the average CO2 storage capacity in case of optimistic approach is 24.79 millions of tons of CO2, and for conservative is 9.9 millions of tons. Considering limited storage capacity in the Ragn gravel reservoir formation, even with optimistic approach of capacity calculation, it was necessary to determine the most suitable and economic case for CCS scenario, which includes Vernadska cement plant. For calculation of CO2 emissions, which could be captured, the data recently reported in European emission trading system for 2020 were taken for economic modeling. It was estimated that capacity of molecular structure in Ragn gravel reservoir for 3 plant scenario will be enough for only 13 years, while for 2 plant scenario, Vernadska and Saluste data for about 21.6 years. 1 plant scenario will be enough for whole project duration more than 30 years for all 3 plants, but they will be the most expensive because it will be not possible to share any exploration, transport, storage, and monitoring costs. So here you can see the table with estimation with results. Considering project duration for estimated 3 scenarios and CO2 storage and CO2 transport distance for from cement plants selected along available natural gas pipelines and or along available roads, the most economic and preferable 2 plant scenario was selected for techno-economic modeling. Here you can see the route model from cement plants to the storage sites. So and we selected 2 plant scenario as the most promising. And here you can see model only for two plants scenario. For 2 plant scenario, which includes Budzi Unicem Vernadska and Heidelberg Cement Italcimenti Calusco cement plants, total emissions produced in 2020 was about 1.2 million of CO2. It was possible to capture about 1.1 million of tons annually and 23 million of tons of CO2 during 20 years of project duration. Considering 5% of additional emissions produced during CCS operations, only 21.8 millions of CO2 million tons of CO2 could be avoided during 20 years of the project. The annual flow rate for the pipelines from the Vernatska and Saluste cement plants is less than 1 million tons per year, and distance to storage sites is 125 and 34 kilometers respectively. Therefore, 220 and 180 millimeters diameter of the pipelines will be sufficient. As we're considering CO2 emissions produced and energy costs in 2020, we can expect cost reduction 2% per year for 5 years. So, not focusing on details. So the cost for monitor, you can see estimations here. So annual cost for in millions of tons for each plant. The total transport, storage, and monitoring cost for Vernatska cement plant is 15.1 euro per ton CO2 avoided, and for Italcimenti Calusco that cement plant it is only 3.95 euro per ton CO2 injected. So, and let's see conclusions. The total CO2 storage capacity of the Malos structure based on the conservative approach, considering the average porosity, is 9.9 millions of tons, while the total CO2 storage capacity based on the optimistic approach is 24.8 millions of tons. The most economic and preferable two-plant scenario was selected for techno-economic modeling. Buzi Unicem Vernatska and Heidelberg Cement Italcimenti Calusco Dada with 159 kilometers of pipelines and total 1.2 millions of tons emissions produced in 2020. It is possible to capture, transport, and store 1.1 millions of CO2, million tons of CO2 annually, and 23 million tons during 20 years of the project into Malosa structure, considering limited CO2 storage capacity of the Sergano gravel reservoir formation, with estimated average optimistic capacity of 24 million tons of CO2. It was estimated that capacity of Malosa structure in Sergano gravel reservoir for 3-plant scenario will be enough for about 13 years, while for 2-plant scenario about 21.6 years, and 1-plant scenario will be enough for whole project duration more than 30 years. Considering 5% of additional emissions produced during CCS operations, only 21.8 million tons of CO2 could be avoided during 20 years of the project. CO2 transport, storage, and monitoring costs for this scenario is the most economic for Italcimenti Calusco that cement plant, estimated as 4 euro per ton CO2 avoided, explained by close location to Malosa storage site. About 34 kilometers of pipelines along available natural gas pipeline will be constructed. CO2 transport, storage, and monitoring cost is 15.1 million tons of CO2, about 4 times more expensive for Vernatska cement plant, explained by 4 times longer pipeline distance and needed CO2 recompression. For more economic scenario for Vernatska cement plant, it is highly recommended to use depleted gas field of any located in the conglomerate Corte Maggiore field in Piacenza, located only 30 kilometers from the Vernatska cement plant, and with good options for CO2 use for enhanced oil recovery. The total cost for the CCS scenario will depend on the final cost of calcium looping CO2 capture at the Vernasca at the end of the Cleanker project. At the present time, the cost at the reference calcium looping capture is 58 euro per ton of CO2 avoided, but could be cheaper for Cleanker pilot at Vernasca. The maximum total CCS cost for Vernasca with the transport and storage in Malosa site could be 73 euro per ton CO2 avoided and will be feasible for CO2 price in European emission trading system of about 75 euro. However, if calcium looping capture cost is 40 euro per ton CO2 avoided will be reached and the storage will be made at the nearest available Corto Maggiore field, then CCS scenario will be feasible starting from about 45 euro per ton CO2 in European emission trading system, or even less if will be supported by CO2 use for enhanced gas and geothermal energy recovery from the depleted gas field. I think it is done. Thank you for your attention. If you have any question, please don't hesitate to ask. According to economic modeling, Alla is more convenient to answer. We will ask her to reply according to all technical questions and geological questions. Please ask.
Thank you, Kazbulat. Thank you so much for this interesting presentation on number of options for transport. I see no open questions at the moment. I have one myself. You mentioned that, which is something quick. You mentioned the need for recompression in the case of the transportation of CO2 from the Buzzi plant to the Malosa reservoir. What is the maximum distance that CO2 can travel typically before it needs a recompression? I mean, is there a standard or a typical value, or it is always very specific to the pipeline, to the site, to the specific project?
I will answer this question. This depends on distance and CO2 flow. So, right. And also at the diameter of the pipeline.
Of course.
So the question is that if we make a smaller diameter for this special small amount, and we have the large distance. So for this 100, more than 100 kilometers that we need recompression. Generally, there are estimated graph. It is not a stable number, constant number. It should be. It could be estimated by available graphs and the tables, and this is dependent of CO2 flow and distance. So you see, we have 125 kilometers, but diameter. Our diameter is not overestimated. It is just for this CO2 amount, because, for example, in Canada, they built from the beginning overestimated diameter of pipeline in order to include more CO2 emissions. And if you have a larger diameter, then it's better. So generally, this recompression depends of CO2 volume and for distance, and so more distance, then the most probable that you will need recompression.
Yeah, of course. But there is a typical range of velocity of the liquid CO2 in the pipeline, typically, or
velocity? I don't know.
I don't know, because this is what determines the need for recompression, I guess.
No, the velocity is not a parameter which is included in these calculations. In calculation is including the pressure drop, and the pressure drop depends on distance and volume. And
so it depends on velocity, right?
Also, it is depend on the initial pressure. So we got parameter 11. for pressure, 11 megapascal, which will be made in Vernazka. And if we're starting from 11, and with this parameter, we will need a compression. Maybe if we start with 15, maybe we will no need a compression. It depends also of the compression number at the capture plant.
Okay.
So we have recalculated from 11 megapascal.
Okay, thank you, Alla. There is another question here from Alessio Pierro asking how you design the transport. Well, first of all, there are congratulations for the nice presentation to Kazbulat. And the question regards the design of the transport system. I mean, how did you select size, materials, operating conditions? What were the criteria?
Yes, generally methodology, we especially develop methodology for all this estimation for Cleanker project. And methodology is based on the report of report from electric industry, which included CCS from Australia, 2015, where they collected a lot of data and prepared a lot of blocks, graphs. And so we used approach from this Australian report, because Australia is a country with many pilots experience in CCS. And so for we use recommendations, graphs, blocks, formulas, mainly from this Australian report 2015.
Okay, which is mentioned in your presentation?
Yes, yes.
Okay,
yes.
Thank you. Thank you, Kazbulat again. Let's move to the next presentation. Now we are lagging a little bit. The presentation will be given by Alla again on the techno-economic modeling of the Baltic CCUS onshore scenario. Alla, I would ask you if you can to maintain the presentation within 15 minutes.
Okay.
If you can. Thank you.
General, the story is that in Estonia we have 8 large emission sources, which made Estonian emissions. But during last years, these emissions are decreasing, because Estonia was until 2019, Estonia was large country exporting energy, but now we have a shortage of energy and we importing energy. So our Energia company, national company, decided that the way to stop emissions is to stop energy production from Estonian oil shales. So, but because Estonia still needs energy and we buy energy from other countries, it needs that we produce leakage of CO2 to another countries, because energy which we buy from our neighbors, they are produced with CO2, of course. So we propose scenario for our largest, for 6 largest CO2 producers from Estonia and Latvia, with CO2 mineral carbonation of Estonian oil shale ash produced by 3 Estonian plants, with pipeline transport of captured and compressed CO2 to North Bleedene structure in Western Latvia. And for techno-economic modeling, there is data and methods. We collected data in ArcGIS. We used building blocks data sets, just the question which was just asked from me. The same methodology for Baltic scenario and Italian scenario. So building blocks to estimate parameters and costs for transport and storage from this April 2015. It's Australian report from the energy industry. So we calculated all costs proportionally to CO2 flow of the plants. So we applied a number of different parameters, which I'm not speaking now, numbers, and we estimated some costs which were estimated earlier were applied. So for CO2 capture and compression taken from our modeling 2011. And we used also proposed numbers for emission allowance price, 40 euro per ton, and the cost for direct mineral carbonation by oil shale ash. We also get a ready number calculated by other authors for other ashes, but similar conditions. And though there is formulas which were applied, what is important here, that when we estimated total cost for 1 ton of CO2 injected or emitted or avoided, we use capital cost, operation cost, monitoring cost, and energy costs. So you can see here all our emission sources with emissions which they annually produced, and also mineral carbonation parameters. We in this scenario, we're applying CO2 use for mineral carbonation, and the mineral carbonation plant will be at the ST power plant. So another ST Energia plant, our located very close, 1 kilometer from ST power plant, and Baltic power plant, also from the same company, located a little bit more distant, but still close. And so the plant will be at ST Energia. Emissions for CO2 mineral carbonation will be at ST power plant, but oil shale ash will be taken from all these 3 plants, ST, Alar, and Baltic. And this is our storage site. I will tell more details on this. Yes, this is the story about our storage site. So here you can see the structural map of storage site. And this is top of our reservoir. Our reservoir is the Cambrian Series 3 Dimena Formation sandstones. And this is Dimena Formation is covered by cap rocks, Ordovician Zebra Formation, Lower Ordovician, which is a clay carbonate rocks. So there is some 2-dimensional and 3-dimensional models constructed for these Blidina and North Blidina structures located in Western Latvia. And here is parameters of the Cambrian Dimena reservoir and another section, geological section of the structure. And the top, so this, as you could see, the structure has 2 parts, and the North Blidina is larger area and it is open from one side, but the smaller part, Blidina, which is lower, located lower, it is deeper. It is closed from all sides by faults, and it is borders. So it is lower area, it is closed, it has smaller parts, smaller capacity. And so we can see the all parameters. So the depth of in the North Blidina more than kilometer, the thickness about 50 meters. So net to gross rate is very good. So the temperature in our Baltic structures in Latvia is rather low at such depths. It's about 20 degrees Celsius, but for CO2 storage, it's good parameter. And we have good average porosity, 20%, and we have average optimistic storage capacity about 267, and conservative about 30 million tons. And so, conservative about 36, and for smaller part, 30 optimistic, 18 conservative. So generally, in our scenario, we applying CO2 use option as CO2 mineral carbonation, CO2 use for mineral carbonation. And because now we took data for modeling from 2019 where energy production decreased, so oil shale use decreased, but still we have a lot of oil shale ash produced, and we estimated that 3.8 million tons of oil shale ash produced at 3 East Energia power plants could be used for mineral carbonation. So 250 kilograms of precipitated calcium carbonate could be produced from 1 ton of oil shale ash, and about 1 million ton of PCC could be produced, about 30 million tons during 30 years, and 110 kilograms of CO2 per 1 ton of oil shale ash could be avoided. So we calculated that about 0.4 million tons of CO2 could be carbonated, altogether 12.6 million tons for 30 years. So generally we calculated parameters for all our plants and percent for the total scenario, and this percent, because our plants will have the total pipelines, this percentage we use to calculate share of costs for the common infrastructure. So generally, the total emissions is more than 7 million tons. About 500,000 tons will go for CO2 mineral carbonation. So captured CO2 will be a little bit more than 6 million tons, and just around 6 million tons could be avoided during year and 180 during 30 years. Our scenario is planned for 30 years. So we calculated parameters for pipelines, the same methodology as reported by Kazbulat. So generally, we have different pipelines. The smaller pipelines is from plants to the common pipeline, and the distance, the maximum distance of the common pipeline is designed for 710 kilometers and for 6.3 million tons of CO2 flow. So, as I told, parameters calculated according to CO2 flow and distance. So we estimated that we will need recompression because large distances, and we are planning 4 injection and 2 monitoring wells for storage and monitoring. So, and the capital cost for all wells, including injection and monitoring wells, is around 18 million euro. And so we estimated capital costs, operating costs as 40%, and annual monitoring costs, energy costs, and so altogether we got such numbers for transport and storage costs for every plant. So the highest is for ST Energia plants, one number for all, and the cheapest, of course, the lowest for Latvia Energia because it is located the closest to the storage site. So, and for mineral carbonation, I already told you that about these technical parameters, and there could be revenues avoided. 40 euro emission allowance price, 40 euro, which we decided to take, and 3 euro per ton oil shale ash for oil shale ash disposal, which is needed to pay if we use it, then we save this money. And we estimated possible market price for high quality precipitated calcium carbonate as 50 euro per ton. And so, just 1 second. Yes, and so we estimated the cost of 50 euro per ton CO2. So the annual costs, also we will have transportation costs for oil shale ash from 2 plants to mineral carbonation plants for 1 kilometer and for 21 kilometer from Balti. And transport, we have that transportation by trucks is 0.07 euro per kilometer per ton of oil shale ash. So we have costs, we have estimated revenues, and revenues minus cost for mineral carbonation is about 70 million euro. So generally we came to results, total economic results for CO2 use, transport and storage scenario, that we got the final balance, which shows that for the Heidelberg cement, Kunda cement plant, we will have costs for 5 euro higher per ton for 5 per 1 year for 5 million euro higher. So we will be in minus 5 million euro per year because there is no CO2 use options and because there is large distance transport. So for the ST Energia plants, because we have CO2 use options and benefits from PCC, we can have at least 24 million euro per year benefit. And for VKG Energia, we will be in minus because no CO2 use modeled, planned. But for Latvia Energia, the cost of energy, if we have 40 euro for CO2 emission allowance price, then the total we can even come to the plus about 4 million euro per year. And so we will, the project will be even beneficial using only benefits from emission allowance price. So in order to come to zero balance, we need about 50 euro per emission allowance price from EU ETS for VKG Energia and Heidelberg cement. And conclusions. So generally, Estonian, Latvian transponders CCS scenario include cluster of 6 largest CO2 producers, including 1 cement plant from Estonia, it's Kunda cement plant, 5 power plants from Estonia and Latvia, 1 cement and 3 energy companies will take in the project, and it will include CO2 use for mineral carbonation of Estonian oil shale ash and production of high quality precipitated calcium carbonate. So annually, we can capture about 7 million tons of CO2 transported and injected, including 6 million tons avoided using transport and storage, and also 0.4 using mineral carbonation. And during 30 years, more than 200 million tons could be captured and 193 avoided. So this, we can use 3.8 million ton of fresh oil shale ash and 0.5 million ton of CO2 for mineral carbonation. And mineral carbonation plant will be a ST Energia power plant, and oil shale ash will be transported from 2 power plants to mineral carbonation plants using trucks. And 6.4 million tons of captured and compressed CO2 will be transported annually for offshore CO2 storage site in Latvia to North Brittany via pipelines. Small pipeline of smaller diameter and 120-250 millimeters diameter from plants, and 1 large common pipeline with maximum 710 kilometer length and diameter of about 700 millimeters will be built during 2 years of construction period. And CO2 will be injected into the 50 meter thick Cambrian series Demena formation reservoir sandstone at the depths more than 1 kilometers. We are planning for injection, 4 injection and 2 monitoring wells. And the monitoring program will according to European CCS regulations, we will need in total 40 monitoring campaigns, including 30 years post-injection period. So we got total average transport cost for scenario about 80 euro per ton CO2, the lowest cost 5.5 euro per ton CO2 for Latvia Energia, that's power plant because it's located at the smallest distance, and at the price 40 euro per ton of CO2 and 50 euro per ton precipitated calcium carbonate, our scenario could be beneficial for 3 ST Energia and Latvia Energia power plant. For Kunda plant, for Kunda cement plant and Vetoga Energia plants without CO2 use options, we will need emission allowance price of about 50 euro per ton CO2, which will be needed to cover all CCS costs, including capture, compression, and monitoring. And thank you very much. References and our project. Thanks.
Okay, thank you, Alla. Thank you for one more interesting presentation. We have a couple of questions that we can address right away. One is from Lawrence Griffin. How come that only a small part of the captured CO2 is utilized for PCC production, precipitated calcium carbonate? Is this based on PCC market size?
What was can you repeat beginning of the question?
The question regards the fraction of the captured CO2 which is utilized for the production of precipitated calcium carbonate. Why not more?
I see. It was based on the available fresh oil shale ash produced by 3 Estonian power plants, which could be available because about 10% of oil shale ash is used for another purposes, and we took numbers which from 2019. For example, if we use numbers from 2018, when we produced too much more energy at this plant, then we would be able to use too much more oil shale ash. So just oil shale ash, which was available in 2019 at 3 power plants.
But the fresh, let's say, oil shale.
Fresh, yes, only fresh, only fresh. We still can use also old oil shale because we have such kind of artificial mountains around our power plants with this oil shale ash, like storage. And if it is not enough fresh, but we would like to use more, we can do it using old oil shale ash, of course. But in this scenario, we made modeling only for fresh ash because to apply old ash, it is more complicated story.
Okay, that's clear, that's clear. And then we have one more question from Emmanuel Muraka, who is asking whether the routes and the CO2 storage, the routes followed to get to CO2 storage are available online in ArcGIS.
I see. In reality, we are planning to do the data available online, but it is not yet ready. It will, maybe we will do it by the end of the project. Okay. So generally, we have plans to make availability online for collected data, but it is not yet ready for online approach. Yes,
we get ready by the end of the project. Okay, thank you again, Alla. We have one more presentation. We are lagging a little bit behind, but not that much. So let me give the mic right away to Kazbulat again, who will deliver us the last presentation on innovative synergy CCUS and renewable energy project offshore Baltic using CO2 emissions from the cement industry. Please, Kazbulat.
Thank you very much. Trying to share again with full screen mode. Can you see everything good?
Yes.
Perfect. Okay, thank you. So I will prepare my screen here. Glad to introduce the update of my PhD study. That was the first, as Stefano said, that's first and only one in the field of CO2 geological storage and petrophysical modeling of CO2 geological storage in Estonia and Tallinn University of Technology. And it is a big pleasure for me that Cleanker project gave me opportunity to make this update of my study on the roof of the project. So this is my, how to say, baby, my favorite structure that I'm already 5 years updating and making it more profitable, adding some new innovative technologies. And I hope that this concept will be useful also for the Italian scenario that I presented, because the situation is very similar, but a little bit revert of the location of storage formation. You will see. So our Baltic offshore scenario is ambitious and innovative, considering proposed new CCUS technologies, ecological synergy using renewable energy, including CCS, CO2 EOR. This is the enhanced oil recovery with using CO2, wind and solar, and the geothermal energy recovery in one storage site. So next is ambitious moment is large storage capacity in the structure, and including a cluster of emission sources from cement industry and energy production from Estonia, Latvia, and Lithuania. So advantages of this concept is reduction of greenhouse gas emissions. First, second, economic profitability, increased CO2 storage capacity, because we have two formation levels in one storage site, and public acceptance. So, and we will meet win-win with 4 times win situation. So here's some geological background. You can see that the main storage formation is Daimena Cambrian formation, located at the depths of 848 meters with thickness of 53 meters, with good storage parameters, reservoir parameters. And on the upper part, at the depths of 700 meters, we have 10.5 thickness meters of thickness Saldus Artificial formation with oil reservoir. And this is quite unique situation, but very close and similar for Italian case. But in Italy, we have vice versa. The storage reservoir up of the storage site, and on the bottom we have oil reservoir. So CO2 emissions produced in 2019 and reported, and European trading system were used for the CCUS scenario. The methodology developed by Cleanker project for techno-economic modeling of CCUS scenario was applied. All geological and technical data needed for scenario modeling were collected into ArcGIS based system created for the Cleanker project. For the definition of technical parameters, we have used Australian power generation technology report, as Alla already mentioned. Spatial data were collected and the map was constructed using ArcGIS platform. The storage capacity of the diamond formation in the E6 was estimated with different levels of reliability using Bachu et al. Method, and theoretical storage potential of oil-bearing Saluste formation at the end of CO2 EOR cycle, implementing conservative and optimistic approaches, evaluated using equation presented also in Bachu. Here is a scenario. It is proposed to capture CO2 from Kunda Nordic Cement plant and from the Estonian power plant in Estonia. So you can see on the map EPP, it's the Estonian power plant. After CO2 will be captured, it will be transported by pipelines to the port of Sillamäe. And the distance is about 30 kilometers. And then by ships will be transported to the port of Kunda, where it will be met by CO2 captured from Kunda cement plant and transport the same 30 kilometers by pipelines to the port of Kunda, and then by ships 615 kilometers by ships to the storage sites in offshore Latvia, that located about 30 kilometers from the Latvian shore. And from the Latvian TETS-2 power plant, CO2 will be transported by pipelines to the port of Liepāja, covering about 230 kilometers. And Lithuanian Acme cement plant CO2 will be transported to the port, the same port of Liepāja by pipelines, covering 145 kilometers, and then by ships it will be transported by to the structure, covering from 30 to 45 kilometers. And here you can see the concept of the E6 structure. So it is considered to drill 6 wells, 3 wells for injection of CO2. 2 wells will inject CO2 to the diamond formation storage sites for CO2 geological storage and geothermal energy recovery, as you can see here, and 1 well to inject CO2 to the oil formation for enhanced oil recovery and CO2 storage in the end of the cycle. And 1 well is planned for geothermal energy recovery to recover warm water, and 1 well from the Saluste formation to recover oil and CO2. And 1 well is planned for monitoring. Also we planned to install the floating wind farms around the rig, and all 3 surfaces of the rig will be covered by solar panels. In this concept we are using 5 different green circular economy techniques: CGS, geothermal energy recovery, CO2 EOR, solar energy, and wind energy recovery. This concept will maximize efficiency of the project, of CCS project, minimize the carbon footprint of the full chain process, and demonstrate win X situation, where X is the number of additional benefits of the project. According to the details, it is planned to capture, transport, and isolate about 175.2 million of tons of CO2 from the atmosphere produced by Estonian Kundot cement plant and Estonian power plant, Latvian TETS and Lithuanian Akumet cement plant during 30 years of the project duration. And the captured CO2 is planned to transport by pipelines and ships. The total distance planned to be covered by pipelines in Estonia, Latvia, and Lithuania is 409.5 kilometers. The total distance for all emissions from Estonia, Latvia, and Lithuania planned to be transported by pipelines and ships together is 1,143.5 kilometers. So 6 wells were considered to be drilled, as I said. Small wind offshore floating plant is planned to be installed around the rig, and solar panels will cover all the available free surfaces of the rig. Produced solar and wind and geothermal energy will be added to the project electricity net to cover energy needs of the project. For example, CO2 injection, fluids recovery, separation, and the CO2 reinjection, and or for selling energy outside the project to the electric grid. And also we have more ideas how we can use energy gained from the project, but it will be topic for the further studies. Our Baltic offshore scenario is ambitious and innovative, considering proposed new technologies, synergy with renewable energy, techno-ecological synergy, large storage capacity, and included cluster of emissions sources from cement industry and energy production from Estonia, Latvia, and Lithuania. These all listed facts make this concept unique and pioneer in the region and in the CCUS and greenhouse gas emissions field of study. And if you are interested in details of the study, you can find it using this link. This study just was presented at the world famous Greenhouse Gas Technology Conference that was made virtually this year, but organized by Khalifa University of Abu Dhabi. So thank you very much for your attention. I hope that we can maybe use this concept further in Italian scenario also, because we have very similar conditions in Malosa structure.
Okay.
Thank you.
Thank you, Kazbulat. Thank you also for compressing the presentation, stimulating ideas. We have one question from Suzanne Harter that thanks for the overview on this ambitious project. And she asks about dynamic flow modeling of CO2 injection to evaluate the injectivity and decide the number of wells which are needed. Is this modeling something that you have done, and will it be available in the report?
Unfortunately, no. We are planning a long time ago to make a dynamic flow modeling, but and we planned this with Scotland University. Hereford University, but unfortunately it for my postdoc, but unfortunately it wasn't realized. So we have planned. Yeah, now this is like more like a concept. Yes, if we needed to realize this concept, of course we need a fluid flow modeling, and then we will estimate real numbers, real number of wells and extra. And number and volume of CO2 available to be injected into the reservoirs and injected and recovered.
Okay, okay. So this is the concept, but there is more work to do in terms of modeling and understanding how it could be done. Thanks again, Kazbulat. Now we would have 10 minutes of conclusions from Alla. but since we are lagging behind, I would ask Alla to conclude just in few minutes, so to leave time for discussion and for the contribution of the panelists. Let me anticipate and thank them for their presence this morning. We have 3 distinguished panelists that will be available for the discussion. Antonio Clausi from Heidelberg Cement Group, Alar Saluste from Ragn Sales, and Raimo Poom, I don't know exactly the pronunciation, sorry, who is a political editor, who the 3 of them are all present this morning, and they will contribute to the discussion, which will start right after the brief conclusions from Alla. Alla, if there is something.
I have really 1 slide of conclusions, not for 10 minutes, much shorter.
Okay.
So, which is mostly conclusions from our presentation. So, according to International Energy Agency 2020, without CCS technology, it is not possible to reach climate targets by 2050 and also by 2070. In the sustainable energy scenario, CCS will support about 15% of CO2 emissions abatement. CCS will play especially important role in such future technologies as direct air capture with CCS, bioenergy with CCS, and hydrogen production with CCS. So CO2 cluster and hubs can help in cost reduction by sharing infrastructure and monitoring costs, and also to improve public acceptance, because many partners included, a lot of working places added, etc. CO2 use options can help to cover high cost of new technologies, but the input in decreasing CO2 emissions is maximum 10 or 8% in all scenarios. Less than 10%, I would say. CO2 use for mineral carbonation of waste, such as Estonian oil shale ash, is environmentally friendly technology, able to neutralize alkaline waste and to produce instead of it useful byproducts like high quality PCC with available market options, or carbon neutral, carbon-free concrete at the cement plant, or it could be also other products. In all CO2 transport and storage scenarios, the most expensive is transport cost, which is increasingly proportional to the transport distance. Therefore, the most economic project is onshore CO2 storage close to CO2 emission source. In case of transboundary projects and larger distances, revenue from CO2 use options can make project beneficial together with revenue from emission allowance price. As the most expensive part of the CCS value chain is still CO2 capture, the total CCS cost will be decreased after wide implementation of CCS technology. We know about learning curves in economics. I will show 1 slide about this. So such decreases are already reported by Global CCS Institute. And this is a possibility for decrease of learning of capture cost using learning rates. You see that at the old studies, the costs were from 50 to 110 euro per ton CO2, United States dollars for ton CO2 for CO2 capture at the coal-fired power plants, and at the studies projects estimations for 2025-2027, the cost already from 35 to 45 United States dollars. So it means that using this learning rates, this low line will come later. We can reach really 30 United States dollars per ton, or it means in euro lower prices. And synergy of CCS projects with renewable energy technologies are looking very prospective, with many win-win situations, which could improve public acceptance, more efficient recovery of geothermal energy, oil, gas, increase CO2 storage capacity, and more safe CO2 storage. Generally, this is all for conclusions, and we can move to discussion.
Okay, thank you, Alla, and thank you for all speakers, Mustafa and Kazbulat. And before starting the discussion, I need to thank also Amici della Terra, partner of the Cleanker project, who set up this Zoom webinar. Many thanks again for your effort and your commitment to the project. And also let me thank also Buzzi Unicem and the Italcementi Heidelberg group for the contribution and the commitment they are giving to our Cleanker project, and more general to the cause of finding a more environmentally benign way of running the cement production. Now, as I anticipated, we start the discussion, and I thank again Mr. Clausi, Saluste, and Poom for their participation to this webinar, their contribution as a panelist. I see no open questions yet, so why don't we start with a round of a table? We do not have a physical table at which we are together, but let's use this image anyhow, asking to the panelists their comment and their view of how they envisage at the moment the evolution of CCUS for the cement industry. Mr. Clausi, do you want to start?
Yes, yes.
Position?
Yes, sure. So good morning, good afternoon to everybody. First of all, thanks for the invitation, and congratulations to, let's say, the nice, very comprehensive presentations that were very interesting. So interesting for me that you know, especially you touch so much the cement industry problems, because maybe we have to underline again that the 60% of our emissions are coming from calcination, from our process. So even if in the future we switch to other fuels like hydrogen, we cannot fix completely our CO2 emissions. And it's very interesting the efforts that you are doing, and not only to capture CO2 and but also the mineralization. I think this is a very interesting topic for the cement industry, how to utilize CO2 in our business. So we as Heidelberg Cement, we are running several projects in parallel. Even so, we have big projects to capture a huge amount of CO2. So your presentation, you name Breivik in North Europe, that now is under execution. 400,000 tons of CO2 per year will be captured and stored in the North Sea. Edmonton in Canada, 600,000 tons per year of CO2. And the third one would be Kazbulat, 800,000 CO2 per year in the UK. And some other projects are ongoing. We are participating on calcium looping, oxy-fuel, Leyland project. So there are many initiatives in parallel. I think what is very important that we are working together. So with the other cement producers, with in touch with universities, association, etc., etc. I think this is very important. We have a common problem, and we have to find together the solution. So this is just my comment in general. Maybe one topic that I would like to highlight that maybe was missing a little bit in the presentation is the CO2 quality. Which CO2 quality we need for storage, especially thinking that we have to collect the CO2 from many CO2 providers, from many different processes. So I think the CO2 quality is quite, an important topic to be addressed because, also minor elements play a role. How to handle the storage.
Okay, yes, CO2 quality is certainly an important issue. Alla.
Can I comment? Yes, the comment for this is that we did not discuss this issue. Of course, it's important, but in general, it's regulated by European Commission Directive on CCS, on CO2 storage. And the CO2 should be of high quality, of very high purity, and it is regulated in all countries according to European Union CCS directive that very, very low amount of admixture is permitted, maybe maximum 1.5% of different. Also, there is now developed another regulations, which is also, I would say, is not only European, but international regulations, which is defining the technical parameters for all CO2 storage parts. And I think that why we did not discuss this, because we think that according to international regulations and European regulations, the CO2 will be of the high quality with very, very small limited permitted admixture. And the quality should be so high that you can use, that it should be like food grade quality, 99% of purity about. Yes, but of course, it could be different issues in different power plants. But it is a matter of work for capture people to reach this purity, yes. And our part is generally mostly use transport and storage. So, for example, for CO2 use for mineral carbonation, we can use even flue gas with not concentrated. CO2 can be taken just from flue gas, or it could be captured also and concentrated. In both cases, this high purity PCC product, precipitated calcium carbonate, will be produced. Of course, during this process, different technological approaches could be added to make this product of the higher quality, higher cost, etc., etc. But it was not just the target of our studies. Yes, but in general, in order to combine different CO2 from different producers, we think it will be of very high purity. If it is not pure CO2, it is not permitted to inject it underground.
Yes. Okay, and thank you, Alla. Thank you. The time is going fast. So yes, let me give you, we have a question coming up, but first let me give the mic just for a short, to say a few words to the other two panelists, Alar, Saluste. Why don't you go ahead giving your view of what is lying ahead?
Hi, thank you. Yeah, first of all, I'd like to say thank you for inviting me to this very interesting seminar. And I think what also was mentioned here today is that the collaboration is the basis for everything. And I really like the presenters' view or maybe even out of the box view of kind of tackling the carbon problem. And Ragn Cells is focused on circular economy and kind of through that also saving the CO2 emissions from happening. But we think that such large-scale ideas and large-scale collaboration is the only way forward for the future. So we are able to produce raw materials in our case, from waste, in order to sustain the economy. But I also have maybe a short question to Alla about the capital cost of this Baltic region solution. I really liked the idea, but what is included in this 70 million that you mentioned? Is it so basically you need CO2 purification, you need from flue gas, you need a pipeline, you need to compress it, and then you need to inject it.
You
Thank
mean do you mean mineral carbonation part?
Also, that what was included in the 70 million? Which parts of capital cost?
For all the project or for mineral carbonation part?
I mean, for the capture, the whole scenario. You mentioned that 70 million of capital cost.
No. The question is that we in this economic modeling, we did not estimate the cost of capture. We took ready numbers of cost of CO2 capture per 1 ton CO2, which we estimated in techno-economic modeling, which we made in 2011 together with colleagues from the Netherlands, who are experts in capture and storage and everything. And at that time, the cost which were estimated for capture per 1 ton, we took this as 25.6 and additional 2.8 for compression. Yes, if we take mineral carbonation part, yes, we in this scenario we took the option if we make CO2 mineral carbonation with flue gas, flue gas and oil shale ash together, and reaction is going, and the cost per 1 ton of CO2 in this very similar conditions was estimated in the master thesis, in the publications, and we use the ready numbers, and they got for our conditions, which close to our conditions, 15 euro per ton CO2 for mineral carbonation, for 1 ton CO2.
Alla, sorry to interrupt you, but we have just few minutes left. I would like to leave the room. Well, first of all, to Raimo, as a political editor, could you share with us your view of what's ahead of us in this field?
Thank you very much, and also it's been a huge pleasure and honor to be invited to listen in and look into this. I'm a journalist. I'm looking at a very sort of basically from an ordinary, perhaps a little bit more than just an ordinary person, but very ordinary person's view. And what amazes me is you know, we deal with climate change issues in our work every day, and there's tremendous interest from readers in how we get a better environment, how we tackle these issues. And what amazes me is that how I see how the industry and how the scientists and experts here are you know, working at such an interesting and innovative ideas, looking ahead, what would be the next steps when the conditions are ready to accept the next steps. And you know, I was listening with great interest, and what I see ahead is that the industry, for example, cement industry, is taking huge steps to look at the future, because you know, while people are interested in climate change and stopping climate change, they will still want to live somewhere. They will want to build houses. They will want to have better cities, and you need cement, and this and the CO2 emissions issue, as was said here, is a sort of a non-avoidable issue. You have to deal with that in that sense, I think, you know, looking at that, there are great stories to be told actually for people, and how the vital industries could survive and could actually even thrive in 50 years, 70 years, and so on. But if I could have a very small question to the end for the experts. From the slides, I saw that, you know, the CCUS and CCS technologies prices are coming down, but still we are looking at, you know, on the ETS price range 50 to 70 euros when these new ideas would become feasibly price-wise for industry commercially. A big part of this was transport. And every project needed a new pipeline or something like that. In Alla and Kazbulat used then in their presentations different sort of modulation. One was pipeline, one was ships. What are the latest ideas for CO2 transport? Are there new ideas that would make the transport cheaper? Is the ship cheaper than the pipeline? Just it's sort of an interesting thing. Can we use existing pipelines that perhaps are not used in the future because we use less gas or less oil? Are the ships, we transport LNG? Perhaps you know, there are ships available that are cheaper. What are the latest ideas on transport? How to make this cheaper? So
transport. Alla, Mustafa, Kazbulat, can you tell us something?
In general, the cost for ship transport, for offshore transport, depends on the distance and amount of CO2 flow, amount of CO2 you transport. And so if you have, of course, if you have very, very large distances, then it's better to use ships. But if the distance are not so large, then even offshore pipelines is better. For example, the approach which is used in the Northern Lights, they will use ships for larger distance, and you can transport from Estonia, from France, from UK, from every country by ship. But then in the port, all the CO2 will be collected together in one surface reservoir. And after that, it will be transferred by offshore pipeline to the storage site. Such approach is the cheapest they found. So if very large distance, then better ship. If the smaller distance, then pipelines, onshore, offshore. And for now, there is discussion for onshore that you can use trains and trucks also. Everything is possible.
Thank you. Thank you, Raimo. And Alla, this issue of the cost of transport is something which is evolving, Raimo. So there are, the figures are being updated, and there is still a lot of work to do to have a mature estimate, let's say, of the costs. We are at 12:30, but let me try to address a question that we got from Aaron Fuller, following us from YouTube, who is asking why, regarding the first presentation about carbonation, why is free lime in pulverized firing ash only partially used? Maybe we already addressed this one previously. But Alla or Kazbulat,
this is question for Mustafa. Mustafa, can you answer?
Can you tell us something about the fraction of free lime in pulverized firing ash which is used? Why do we use only part of it? Mustafa, are you still there? No, Mustafa doesn't seem to be here. Can you say something, Alla, about this? Just to give a...
Generally, not questions to me.
Okay, that's okay, that's okay.
We have special research group for this. Okay. They're eligible to answer.
Oh, okay. But we will give an online answer, online, sorry, on the Cleanker website, okay? So Aaron, Fuller, please stay connected. You will find the answer on the Cleanker website, which will give you the opportunity, if you haven't been there yet, to know more about our project. It's 12:32, and this way of being connected by remote makes us much more adherent to the schedule than maybe in a personal meeting. So it is my job now to close the webinar. First of all, thanking the speakers and the panelists for being here with us. And then thanking all those who connected and who followed the webinar, as well as I like to repeat this, Amici della Terra, who set up this webinar. First of all, Donovan Baldassarri and his collaborators. Thanks again for the webinar, and more generally, thanks to Amici della Terra, Tallinn University of Technology, for their participation and their contribution to the Cleanker project. I'm sure that there will be other opportunities for all of us to interact. Please watch the evolution on the Cleanker website. If there will be news and other opportunities, we'll keep you informed. For the time being, thanks to everyone for being connected, and have a nice day, all of you. Bye-bye.
Thank you very much.
Thanks.
Ciao, ciao.
Thank you, everyone.
See you soon personally. Ciao.
Bye-bye.